Ask a modern AI chatbot a sufficiently pointed question about deep prehistory, and you will usually get one of two kinds of answers back. Sometimes you get a flat, cautious summary that hedges every sentence into meaninglessness, but increasingly, when the question concerns one very specific moment in the deep human past, roughly 12,900 years ago, the answer that comes back is neither mythology nor hedging. It is a genuine, actively contested scientific hypothesis, one that professional geologists, archaeologists, and climate scientists have spent nearly 2 decades arguing over in peer-reviewed journals, and one that happens to sound, on first hearing, almost too dramatic to be real science at all. That hypothesis has a name, the Younger Dryas Impact Hypothesis. It proposes that a cosmic object, most likely a fragmented comet, struck or exploded above the Earth's atmosphere at the end of the last ice age, triggering a sudden and catastrophic reversal of the planet's climate, contributing to the extinction of dozens of large mammal species, and quite possibly playing a role in the collapse of one of the earliest known human cultures in North America. It is not a claim about a lost city or a technologically advanced vanished civilization. It is a claim about physical chemistry, sediment layers, and ice cores, and it sits exactly at the point where legitimate, hard-fought scientific inquiry brushes up against the kind of ancient catastrophe narrative that has captured the human imagination for as long as we have been telling stories at all. That overlap is precisely why the topic keeps resurfacing whenever people ask an AI system to explain what really happened at the end of the Ice Age. And it is worth understanding exactly what the evidence does and does not say. To understand why 12,900 years ago matters so much to climate scientists, you first have to understand what the Earth's climate was doing immediately before that point. By roughly 14,000 years ago, the planet had been steadily emerging from the depths of the last glacial period, entering a warming interval known to paleoclimatologists as the Billing-Alerud, during which global temperatures rose substantially, ice sheets retreated, and the world began to look recognizably closer to the one we live in today. Then, with a speed that has puzzled climate scientists since ice core records first revealed it in detail, that warming trend reversed. Temperatures in the northern hemisphere plunged back toward near glacial conditions over a period that ice core evidence from Greenland suggests may have taken as little as a few decades, an almost instantaneous shift by geological standards. This abrupt cold snap, which lasted for roughly 1,200 years before the climate resumed its warming trend, is known as the Younger Dryas, named after a small Arctic wildflower whose pollen shows up abruptly in European lake sediments from this period, marking the sudden return of cold-adapted vegetation to landscapes that had only recently begun supporting temperate forest. The mainstream explanation for the Younger Dryas onset, and still the explanation favored by a substantial portion of the climate science community, involves a massive pulse of fresh meltwater from the collapsing Laurentide ice sheet pouring into the North Atlantic Ocean, disrupting the ocean circulation patterns that normally carry warm water northward from the tropics, and effectively shutting off the oceanic heat delivery system that had been keeping the northern hemisphere relatively warm. This meltwater forcing hypothesis is well supported by oceanographic modeling and by geological evidence of ancient glacial lake drainage events, and it remains, for many researchers, the most parsimonious explanation available. But starting in 2007, a different explanation began gaining traction, put forward by a research team led by the nuclear physicist Richard Firestone and published in the Proceedings of the National Academy of Sciences. The team argued that a thin, distinctive layer of sediment found at multiple sites across North America, dating precisely to the onset of the Younger Dryas, contained physical evidence consistent with a cosmic impact event, elevated concentrations of iridium, an element rare in the Earth's crust, but relatively common in asteroids and comets, alongside microscopic nanodiamonds, magnetic microspherules, and other materials that the researchers argued were best explained by the intense heat and pressure of an extraterrestrial object striking or exploding above the Earth's surface. The proposed scenario involves a large comet potentially fragmenting into multiple pieces, either striking the Laurentide ice sheet directly or detonating in a series of massive airbursts above it, similar in mechanism to, but vastly larger in scale than, the 1908 Tunguska event in Siberia, in which a comet or asteroid fragment exploded in the atmosphere above a remote forest region, flattening trees across an area of more than 2,000 square kilometers without leaving an impact crater. An impact, or airburst event of the scale proposed for the Younger Dryas boundary could, according to proponents of the hypothesis, have triggered rapid melting of the ice sheet, released the very meltwater pulse that mainstream climate scientists already credit with disrupting ocean circulation, ignited widespread wildfires across the North American continent, and thrown enough debris into the atmosphere to trigger a period of significant cooling on its own, functioning as a kind of impact winter layered on top of, or instead of, the meltwater mechanism. part of what made the Younger Dryas impact hypothesis so immediately compelling to some researchers and so immediately controversial to others is that its proposed timing lines up closely with two other major events that had already puzzled scientists for decades. The first is the North American megafauna extinction, the disappearance of dozens of large mammal species, including mammoths, mastodons, giant ground sloths, saber-toothed cats, and American horses and camels, within a geologically narrow window at the end of the Pleistocene. Scientists had long debated whether this extinction was driven primarily by human overhunting following the arrival of skilled big game hunters in the Americas, by the climate stresses of the retreating ice age, or by some combination of both factors, and the possibility of an additional, sudden environmental shock at precisely this moment added a new variable to that already contentious debate. The second is the disappearance of the Clovis culture, the sophisticated stone tool tradition associated with some of the earliest well-documented human populations in North America, identifiable across the continent by its distinctive fluted spear points. Clovis sites disappear from the archaeological record at almost exactly the same boundary layer, where the proposed impact evidence is found, and proponents of the impact hypothesis have argued that a sudden climatic catastrophe, layered on top of wildfire devastation and the collapse of the large game animals that Clovis hunters depended on, offers a coherent explanation for why this particular cultural tradition seems to end so abruptly, rather than gradually fading or transitioning into later technological traditions, as many archaeological transitions typically do. The Younger Dryas, so impact hypothesis, has faced serious and sustained scientific criticism since shortly after it was first proposed, and it would be inaccurate to describe it as a consensus position within geology or archaeology. A prominent critique published in 2011 by the geologists Nicholas Pinter and Andrew Ismail Andronikov, along with several co-authors in the journal Earth Science Reviews, argued that many of the supposed impact markers reported by the original research team, including the nanodiamonds and magnetic microspherules, could not be independently replicated by other laboratories attempting to examine samples from the same sites, and that some of the reported materials were more plausibly explained by ordinary terrestrial processes, such as fungal or algal activity, industrial contamination of samples, or simple laboratory measurement error, rather than requiring an extraterrestrial source. Critics have also pointed out that no confirmed impact crater of the appropriate size and age has ever been definitively located, a significant gap for a hypothesis proposing an event large enough to trigger hemisphere-wide climatic effects, though proponents respond that an airburst event, particularly one occurring above or within an ice sheet that has since completely melted away, would not necessarily leave a crater that could still be identified today. The overhunting explanation for the megafauna extinction, meanwhile, remains, supported by the correlation between the arrival of skilled human hunters and extinction timing across multiple continents, including regions where no impact evidence has been proposed at all, which some researchers argue makes an additional catastrophic trigger unnecessary to explain the extinction pattern. Despite the sustained skepticism, the hypothesis has not disappeared, and in some respects the evidence base supporting it has continued to grow rather than collapse entirely. A 2019 study led by the geochemist Wendy Wolbas and published in the Journal of Geology reported an anomalous spike in platinum concentrations at the Younger Dryas boundary layer found in sediment cores from Hall's Cave in Texas, a site independent from many of the original locations examined by Firestone's team, and one where the researchers argued the platinum anomaly could not be easily explained by volcanic activity, wildfire residue, or other conventional terrestrial sources. Similar platinum anomalies at this specific boundary layer have since been reported at additional sites across multiple continents, including in Greenland ice cores, which some researchers have argued strengthens the case for a genuine, geographically widespread event of some kind occurring at precisely this moment, even as the debate over whether that event was cosmic in origin and how significant its climatic effects actually were remains unresolved among specialists actively working on the question. What makes this an unusually difficult scientific question to fully settle is that it requires reconciling evidence from several entirely different disciplines: ice core climatology, sedimentary geochemistry, paleontology, and North American archaeology, each of which has its own methods, its own standards of evidence, and its own community of specialists who do not always agree, even among themselves, about how to interpret ambiguous or borderline data from a single geological instant that occurred nearly 13,000 years ago. It is worth being direct about where legitimate scientific debate ends and popular speculation begins, because the Younger Dryas period has also become closely associated, particularly in popular media, with a considerably more speculative claim: the idea that an advanced, now-vanished human civilization existed before this catastrophe and was destroyed by it, a narrative most prominently advanced by the writer Graham Hancock, and popularized through various television documentaries and internet discussion. This narrative frequently points to real archaeological sites, most notably Gobekli Tepe in southeastern Turkey, an extraordinary complex of carved stone pillars dated to roughly 11,500 years ago, making it the oldest known monumental architecture anywhere in the world, constructed remarkably by hunter-gatherer communities that had not yet developed agriculture or pottery. Mainstream archaeologists generally regard Gobekli Tepe as compelling evidence that pre-agricultural human societies were considerably more socially organized, technically capable, and ritually sophisticated than earlier models of hunter-gatherer life had assumed, a genuinely significant revision to the standard narrative of human civilizational development. What mainstream archaeology does not generally accept is the further claim that Gobekli Tepe, or any other known site, represents the remnant of a technologically advanced global civilization destroyed by the Younger Dryas event, a claim that goes considerably beyond what the site's actual architecture, artifacts, and dating evidence support, and one that most specialists in the field regard as speculative extrapolation rather than a conclusion the physical evidence itself requires. One of the more physically striking pieces of evidence connected to the Younger Dryas boundary is a distinctive, dark sedimentary layer, often only a few centimeters thick, that shows up at numerous archaeological and geological sites across North America, at precisely the depth corresponding to this moment in time. Researchers refer to it, somewhat informally, as the black mat, and it has been documented at dozens of sites stretching from the Pacific coast to the Atlantic seaboard, generally rich in organic carbon, and, at many locations, directly overlying the last Clovis-era artifacts and the final bones of extinct Ice Age megafauna found at that site, with no later Clovis material or extinct animal remains appearing above it anywhere. Proponents of the impact hypothesis point to elevated charcoal and soot content within this layer at multiple sites as evidence of unusually widespread and intense wildfire activity occurring at this exact moment, consistent with the kind of continent-scale combustion event that a large atmospheric airburst could plausibly trigger. Critics counter that widespread wildfire activity at the end of an ice age, as vegetation patterns shifted rapidly and dead biomass accumulated during a period of climatic upheaval, is not inherently surprising or diagnostic of a cosmic trigger, and that the black mat's organic richness may simply reflect the kind of wetland and marsh conditions that would naturally develop as regional water tables and drainage patterns changed during the onset of Younger Dryas cooling. As with much of the evidence surrounding this period, the same physical observation supports more than one explanation, and specialists on different sides of the debate have not reached agreement on which explanation better fits the full pattern of data. Some of the most precise evidence for how abruptly the Younger Dryas began and ended comes not from North American sediment at all, but from ice cores drilled through the Greenland ice sheet, where each year's snowfall is preserved as a distinct layer, allowing scientists to reconstruct a year-by-year record of temperature, atmospheric dust, and chemical composition, stretching back well over 100,000 years. The Greenland Ice Sheet Project cores, along with several subsequent and even more finely resolved drilling projects, show the transition into the Younger Dryas coal period, and the transition back out of it at its end, occurring with a speed that startled the climate science community when it was first fully documented, with some analyses suggesting the shift into colder conditions took place over a period measured in single decades rather than centuries. This ice core evidence is significant for the impact debate because it establishes, independently of any question about a comet or asteroid, that whatever triggered the Younger Dryas was capable of altering the climate system, with a speed that ordinary gradual changes in solar output or slow shifts in ice sheet configuration would not easily explain, lending at least circumstantial plausibility to the idea that some kind of sudden triggering event, whether an oceanic circulation shutdown, a rapid meltwater pulse, or an added atmospheric shock from an impact or airburst, was involved in setting off the transition, even if the ice cores themselves cannot specify which of those mechanisms, or what combination of them, was actually responsible. There is a broader point worth making about what happens when people turn to AI chatbots for answers on genuinely contested scientific topics like this one. A well-calibrated answer to a question about what happened 12,000 years ago should not sound like a confident revelation, and it should not sound like a dismissal either. It should sound like what a careful science journalist or a working researcher in the field would actually tell you if you cornered them at a conference, that there's real, physical, peer-reviewed evidence pointing towards something unusual happening in the geological and archaeological record at this specific moment, that a serious cosmic impact hypothesis exists to explain part of that evidence, that equally serious researchers have raised substantial and so far unresolved objections to key parts of that hypothesis, and that the mainstream meltwater explanation for the Younger Dryas onset remains very much alive and well supported in its own right. That is a considerably less tidy answer than either scientists have secretly confirmed an ancient apocalypse, or there's nothing here worth discussing. and it is also the accurate one. Any AI system or any human science communicator describing this topic honestly will end up in roughly that same nuanced territory, not because the subject has been artificially inflated into controversy, but because the actual evidence, drawn from ice cores in Greenland, sediment layers across 2 continents, and the bones of a vanished culture in North America, genuinely does not yet point to a single, fully settled conclusion. What makes the Younger Dryas period such a durable subject of both serious research and popular fascination is precisely this combination of genuine, well-documented abruptness in the physical record with a still unresolved explanation for what caused it. Unlike many questions in paleoclimatology, where the broad mechanism is well understood and only the fine details remain to be worked out, the Younger Dryas onset continues to resist full scientific consensus nearly 2 decades after the impact hypothesis was first proposed, with serious credentialed researchers continuing to publish new evidence and new critiques on both sides of the question in current peer-reviewed literature. That ongoing uncertainty is not a failure of the scientific process. It is what genuine scientific uncertainty looks like while it is still being worked out, in contrast to questions that have already been effectively settled and are simply awaiting broader public awareness. The Younger Dryas impact hypothesis may eventually be confirmed by the discovery of a definitive impact crater or by evidence that survives more rigorous independent replication than the original nanodiamond and microspheral findings have so far received. It may instead be gradually set aside in favor of the meltwater forcing explanation, refined by decades of additional oceanographic and glaciological modeling. Or, as with many genuinely difficult scientific questions, the eventual answer may turn out to involve elements of both explanations working in combination, a possibility that a number of researchers on both sides of the current debate have already begun to take seriously. When a modern AI system is asked what actually happened 12,000 years ago, a well-informed answer tends to land in exactly this territory. A real, still unresolved debate about whether a cosmic impact contributed to an abrupt climate reversal, layered against a genuine and remarkable archaeological discovery whose full significance is still being worked out, all of it surrounded by a much larger body of popular speculation that goes further than the underlying evidence currently supports. That is not a dramatic revelation so much as an accurate reflection of where the actual science currently stands, which is itself more interesting and considerably more scientifically alive than either a simple confirmation of ancient catastrophe or a simple dismissal of the entire question would be. The honest answer, in other words, is that scientists do not yet know for certain what triggered the Younger Dryas, whether a cosmic impact played any meaningful role in it, or exactly why the Clovis culture and so much of the Ice Age megafauna disappeared in such a narrow window of time. What they do know is that something genuinely abrupt and genuinely significant happened to the Earth's climate, its large mammal populations, and its human inhabitants within a remarkably compressed span of time, roughly 13,000 years ago, that the evidence bearing on why is scattered across ice sheets, cave sediments, and stone tool assemblages on multiple continents, and that reconciling all of it into a single, fully confirmed explanation remains one of the more genuinely open questions at the intersection of climate, science, and human prehistory. Whatever the eventual answer turns out to be, it is likely to be more complicated and more scientifically interesting than any single dramatic headline can fully capture.